Okay, so welcome to Tutte Colloquium today, and we have speaker Nisheeth Vishnoi from Yale University. So he's a professor at computer science at Yale. His research focuses on algorithms and complexity theory, sampling, and optimization problems. So today he's going to talk about sampling under symmetry.
Thank you so much for the invitation, and it's a great pleasure to be here giving this talk. This is the first time I'm giving this talk, and this talk is about sampling from certain structured manifolds. Structure in the sense that there are symmetry groups, such as certain Lie groups that act on these manifolds. And the punchline is that these symmetry groups enable the existence of some very efficient algorithms for some very classic problems. So this is what the talk is going to be about. Let me start by a very concrete motivation problem, which you can think of as a quantum inference problem. So suppose I give you a density matrix, which is an n cross n positive semi-definite matrix, I guess, with trace 1. And I ask you to infer a pure state. So the density matrix kind of captures the probability distribution of a quantum state. And maybe you want to infer what is the state that this density matrix could come from. So these two, just to set up some notation, the set of density matrices is a convex set, a convex manifold. Let's say it's called D. And the set of pure states is, which are the set of all rank 1 density matrices, or rank 1 projection matrices. This actually is a non-convex manifold. They're related in the sense, okay, this should be M here, that the set of density matrix is the convex hull of the set of pure states. So this is how the picture looks like. You have this thing in blue, which is the non-convex manifold of pure states. There's a convex hull of this, and you're given some state in this convex set, and you're asking what is a state on this blue manifold, where this could have come from. So there's no one answer to this. And one approach to such a problem is what is called the principle of maximum entropy, which says essentially in this situation suggests the following strategy to infer a quantum state, a quantum pure state, is that find a distribution on this manifold M of rank 1 matrices, rank 1 projection matrices, so that the expectation taken over the probability distribution that we are looking for is A, so it has a right marginal. And with respect to that, it maximizes, subject to that constraint, it maximizes the entropy. So before we can talk about a notion of entropy here, we have to talk about a notion of measure. And luckily, this set of pure states, this blue set, the non-convex set, actually has a base measure, which is called the which is derived from Haar measure, and so you can integrate over this manifold and so on. And given that, you can write down the following convex program actually to solve this problem. So let me explain this a little bit slowly. So can you see my cursor just to check? Yeah, okay. So this is a constraint here which says that we're looking for a density nu on this supported on this manifold, which is a density with respect to the base measure mu. So these two things are just enforcing essentially the constraint that we're looking for a probability distribution. This constraint here is the marginal constraint. It says that the expectation of a density matrix, rank 1 matrix sampled from this density is exactly the given matrix A. And this is the objective function. So the problem in this setting is that entropy is not well defined because it has infinite support. But what you can do is instead try to measure the distance of your density or from the base measure or the differential entropy, which is given by this formula, and KL stands for the Kullback-Leibler. It's analogous to the Kullback-Leibler divergence for Shannon entropy. So this is the optimization problem that one could try to solve on this object, whatever it is. The problem with this is that this is an infinite dimensional optimization problem, because what we're looking for is a density which is supported on the entire manifold M. It's not even clear how to go about doing this. But here's the good news, that there is a finite dimensional problem that you can write down by writing down the dual optimization problem corresponding to this. And that turns out to be a problem which is of this form. It's not expected that you understand how we get this dual, but this is not too difficult to get from here to there. The key thing to note is that the objective function is now a function of a matrix, an n cross n Hermitian matrix. That's what we are looking for. So the domain has suddenly become finite dimensional. So there is some hope that we can solve this problem. But by solving this problem, we are not going to get the distribution nu. So we have to understand how to take the optimal solution of this and recover an optimal solution of the primal program. And here we can show that we can see that under some minor technical conditions, which is in this case the fact that the matrix A, which is given to us, is not on the boundary of this convex hull, it's in the interior. Then there is a solution, there is a relation between the optimal solution to the primal program, which is this nu star, and to the dual. And in fact, this turns out to be the optimal density function on this manifold turns out to be an exponential density of this type. So these angles here are a suitable inner product in the space of matrices. It's usually just a trace or the Frobenius inner product. So if you think of matrices as just n cross n vectors, then this is the standard way to take inner product. So I'm not going to go into the details of why strong duality holds and so on, but at a high level, there are two questions that come computationally. This talk is about computing these things. The first is, how do we solve the dual optimization problem? Or how do we compute this Y star? And the second, which is the focus of this talk, is suppose I can somehow compute this optimal dual solution. How do I then sample from this density function? This is not an obvious at all, actually, that you may be able to solve this, but to go from here to there, you need to be able to sample from such a density function. And this is the central problem we are going to study in this talk. If you have any questions about the motivation or anything, please feel free to interrupt and ask. Okay, so let's look at this density function in a bit more detail, and let's zoom out. So this is where the realization that this manifold is not just an arbitrary manifold. In fact, this is a very symmetric manifold comes in. And the manifold we are talking about is a set of rank 1 density matrices or rank 1 projection matrices. So a very basic observation is that this manifold is the union of the following matrices. So let E sub 1 be the matrix which has exactly 1, 1, which is in the 1, 1 entry, and zeros everywhere else. So this is a rank 1 matrix with trace 1. So this is a special, a single point on this manifold. And what we're doing is conjugating this matrix with unitaries. So U is a unitary matrix. So UN is a unitary group. And the claim is that it's a simple claim. I mean, it's obvious if you just think for a minute, that this manifold M is is obtained from conjugating E1 with every element of the unitary group. And these things have a name. And these things are called orbits. And in particular, M is a unitary orbit of this point E1. Okay, so this is just some notation, but I mean, what we have done in this process is observe that this is not just an arbitrary manifold. This is a very structured manifold. And in fact, we can define a very general class of manifolds through this process. So for example, consider any n cross n Hermitian matrix lambda, and you can look at the orbit of lambda, which is generated exactly as before, except that now instead of E1, you conjugate lambda. And we're going to be talking about this manifold a fair bit. So here are some simple observations about this manifold. The most trivial one is that because we are conjugating by unitary matrices, all the eigenvalues of the eigenvalues of all the matrices in this orbit are exactly the same, and the same as that of lambda. And maybe it's useful to just think of lambda as a diagonal matrix, if that is more convenient. Moreover, for people who have some background in this, probably realize that you cannot necessarily define a base measure on any manifold. And so what makes these manifolds even more special, besides the fact that they are orbits, is that you can essentially transfer the Haar measure on the unitary group to these orbits. So there's just this mapping actually allows you to transfer a measure. So the problem, so you can start talking about problems of optimizing over these manifolds, or or talking about sampling on these manifolds. There is a measure. Like there's a very natural measure. Other examples which you might have, which you can already start thinking, is generalization of E1, which is EK, where you have exactly K1s in the diagonal and zeros everywhere else. And this gives rise to well-known manifolds. In particular, things like stifle manifold, Grassmannians, and so on. So I guess this is something that you might have heard of. If you're not from this area, then you might have heard of, but might not have realized that these are actually just unitary orbits, or orbits of something. Okay, so this is a one-slide introduction to orbits. Any questions? Okay, let's move on.
Oh, sorry, there seems to be some questions from Henry. Question: what does V at least 0 means?
Yeah, what do you mean by V greater or equal to 0 for the original problem?
Oh, you mean here?
Yeah, at the bottom.
Yeah, this means that it's a non-negative density.
But V is a function of X, right?
Right, so it means that nu of X is greater than 0 for all X. That's what it means.
And
sorry
X,
for the shorthand.
And X is in what set?
X is in the manifold M. because we are looking for the distribution on the manifold M.
So you have an infinite number of non-negativity constraints.
That's right. And that's why I mentioned that the problem is infinite dimensional. Yes.
And you're saying the only constraint qualification you need is A is in the interior?
For strong duality to hold for this particular convex optimization problem.
Okay.
Does that answer your question?
Yeah, I'm just surprised. But it answers my question. Thank you.
Okay. So this is the computational problem that we're going to talk about. How to sample from a unitary orbit. So the input consists of two Hermitian matrices. One is lambda, which describes the orbit, and one is y, which describes this exponential density on the orbit. So I gave you as a motivation this quantum inference problem, but actually it's a special case of a very general problem considered with my co-author Jonathan Leake in a couple of papers, one that appeared in Stock in 2020, and a follow-up on that we just recently posted. This was the original motivation for us to look at sampling problems of this form. But since then, we have found that these density functions actually are ubiquitous. In fact, in statistics, they are known by a different name. They're called matrix, Langevin, or Bingham distributions, which have exactly this form. So there's nothing else to state than to just rename them. Interestingly, in differential privacy, which is an area, sub-area of theoretical computer science, these distributions also arise. In particular, the point of this talk is not differential privacy, but I'm just going to maybe talk about it for a minute or two to give you a sense of what's going on there. So traditionally, the goal is to design a differentially private algorithm for any problem blah in differential privacy. And one very general approach is what is called the exponential mechanism, where instead of optimizing this function blah, you essentially sample from the exponential of of this blah, which is like the Gibbs distribution essentially in some sense. So a lot of these problems, like low rank approximation problems, which are important in, like you might have heard of this Netflix problem and so on. If you want to design differentially private algorithms for that, they reduce to exactly special cases of this sampling from unitary orbits. Of course, this observation was not made before this paper, just to be clear, that these are actually sampling problems of this nature. And there are several results. I'm probably not citing all of them, but these are two papers which actually try to develop algorithms for these problems. And yeah, I guess the open problem in all of these applications, whether it's maximum entropy inference or statistics or differential privacy, is there an efficient algorithm to sample from such orbital densities? Let me switch gear and introduce a different density matrix, which actually is ubiquitous in physics. These are called the Harish Chandra, after a famous Indian mathematician Harish Chandra, and two physicists, Itzikson and Zuber. So they studied this density function. So this is a density function on the unitary group again. And it looks a bit weird if you first see it. It's the exponential of the trace of yu lambda y star. So this is the density with respect to the base measure mu. Now this is not on the orbit of a special element. This is on the entire unitary. So this is really the orbit of the identity matrix. So what is the relation between this density function and that? I guess before I say that, let me just point out that this is this density function is present in a variety of areas, most of which I don't understand. but it has been used to model various physical processes, or nuclear forces, or models of string theory and so on. And they also show up in mathematics. In fact, Harish Chandra's initial motivation was mathematical, trying to understand classification of semi-simple Lie algebras and so on and so forth. So they have a very central role in mathematics and physics. And the relation between these densities and the orbital densities I talked about in the previous slide is the following. It's very easy to see that if I plug in x equal to u lambda u star is the conjugate transpose of u, then this density is exactly this density here. So it is, so there are two matrices here, y and lambda. I mean, their roles are in some sense symmetric, so it's my choice of lambda was arbitrary, but you can view the Harish HCIZ densities as orbital densities. And the problem of sampling from HCIZ densities was independently important in physics, where people needed to do some simulations based on these things. So I guess these orbital densities have a remarkable expressive power. By specializing lambda, you can start recovering special cases, as we saw in the previous slide. You can also view them as HCIZ densities, and it just gives more impetus to this question of, can we design efficient sampling algorithms for these densities? Any questions? Okay. So this brings us to the main result. This is a very recent preprint with Jonathan Leake and Colin McSwain, both of whom are recent math PhD students, one from Berkeley, one from Brown. And the main theorem is, the following, that we can give an exact algorithm to sample from these density functions. And the algorithm runs in time polynomial in the norm of y and the norm of lambda. And note that these norm dependency is necessary, because what we're really looking at is the exponential of something. So we cannot really hope anything better than better dependence on the norm of these matrices. So you should really think of the input as e to the y and e to the lambda, as opposed to y and lambda. For people of a more TCS flavor in this audience who might be expecting an algorithm that runs in polynomial in the bit complexity of y and lambda, this is not to be expected here. But what is interesting is that, unlike methods that have been developed, I've also been involved in some of these methods. I mean, starting from work of Lowash and others, of sampling from log concave functions or sampling from manifolds. The dependence here on the error is polylogarithmic. In that sense, it's exact. That we're going to sample a density from a density function which is epsilon away from the target, and the running time is logarithmic in 1 over epsilon.
Hey, Nisheeth,
Yeah.
I had a question. I think I lost track a little bit from what you were saying at the beginning, and I'm trying to just center myself around your original motivation.
Yeah.
So in the context of like quantum states,
Yeah.
Can you just remind me, what problem does this solve? Like, you have you're given a mixed state.
Yeah.
And you want to infer a pure state,
right?
Which satisfies what property with respect to the mixed state?
So it satisfies the property that the marginal. So you want. So I mean, instead of outputting one state, you want to output from a probability distribution.
Mm-hmm.
And the property that this probability distribution has is that the marginal is the given density matrix. And that's pretty much the only constraint it has. And given that, it maximizes the entropy of the probability distribution from which you will recover the sample.
So the system is not just like the size of the pure state is larger than the size of the mixed state, and you're taking.
No, it's the same size. It's the
Oh,
same.
but when you say the marginal, I guess I'm confused what you mean by.
Okay,
by
maybe
that.
it's yeah. So maybe I'll show you this first slide just again. Then I'll come back to this. Okay, so this is the optimization problem that I'm talking about.
Mm-hmm.
So you're given this density matrix A. It's an n cross n matrix. Pure states, even though they are rank 1, well, you can think of them as vectors, but I'm representing them as vector-vector conjugate transpose. So it's really a matrix, but it's a rank 1 matrix. So X is also a rank 1 matrix, and that this is the marginal constraint, that the density that you're looking for on this manifold, if I take the expectation of a matrix sample from this density, then it's exactly A.
Oh, I see. It's an ensemble. I see. As an ensemble, it
yeah. So maybe
represents.
I mean I'm not a quantum mechanics person or a quantum computing person, so I might be using a wrong marginal word.
No. Thank you very much. It's very helpful. Sorry for the interruption.
But I mean, the point is that this constraint is not enough to specify. If this is all the information you have about the system, there's this philosophical argument that what should the state of the system be, and that's where you say, given that this is the only constraint. One should look for the density which has the most amount of information, and information measured in the sense of Shannon.
Thanks.
Does that answer your question?
Yes, absolutely. Thank you.
Okay, so let's go back here. So these are the implications of our results. All of these problems that I talked about in the previous slide now have a polynomial time algorithm. And there's nothing mysterious. I mean, these are completely direct applications, so I don't even have to do anything additional. I just have to specialize the algorithm. And for people who are familiar with Lie groups, I should mention that this result actually generalizes to other compact Lie groups. So one thing which is nice about the unitary group is that it's an example of a compact Lie group, or whatever that means. It's a manifold with a group structure which interact nicely. And there are, the classification theorem of compact Lie groups essentially has 3 major classes: the orthogonal group, the symplectic group, and the unitary group. And our result extends for all of these orbits. So I'm not going to define these things, what this means. You're welcome to look at the paper. Okay, so I'm about 30 minutes into the talk, and I want to give you a little bit of flavor of the proof, because I think there are some interesting ideas which might be useful independent of whether you're interested in this problem or not. And so maybe 15, 20 minutes I'm going to spend on proofs. So just recalling the problem. So let's start from the very beginning. How would we solve this problem in the simplest possible case? And the simplest possible case is essentially when there is no exponential here. So this is just y is 0. So this term is not really present. And lambda is identity, which means that this is just asking how to sample a random unitary matrix. And this doesn't require anything non-trivial. You can follow the following process. Sample a random Gaussian vector, normalize it to get a unit vector. If you were just looking for a one-dimensional vector, this would be it. Since we need n of them, we have to keep orthogonalizing and repeating. So just simple Gram-Schmidt orthogonalization, and then the ability to sample from a Gaussian distribution will give you what you're looking for in the simplest case. So this is pretty straightforward. There are serious obstacles to extend this to the general case. It's hard to articulate them, but one reason is that when y is not 0, this additional exponential term that shows up is not unitarily invariant, and hence it's not clear how to induct. I mean, the simplest case is an induct proof by induction, so it's not clear how to induct. And that is really why this problem has been open, because it's not really clear how you're going to do this. I mean, there is this additional, once you start looking into this orbit, you realize that it's not just a manifold, it's actually also an algebraic variety, this object. And in particular, it's described by certain high degree polynomial equations. And that creates a lot of correlation in the entries of the matrices. And it's not clear how to start your sampling process in some reasonable inductive manner, especially when there's no real symmetry or unitary invariance given this additional term. So, well, there are two ways to view a matrix. One is in the coordinate reference frame, which is so far what we've been talking about. But matrices also have eigenvalues, and we could explore that path a little bit. So let's see. What information do we need in the world of eigenvalues? Or is there some information in the world of eigenvalues that will help us get some more, a recursive structure or inductive structure, which will allow us to execute a sampling algorithm? So when you start going in this direction, the first obvious problem is that, this doesn't sound like the right direction, because, as we just observed earlier, all matrices in this orbit have the same eigenvalues. So in fact, if I map a matrix on the orbit to the set of eigenvalues, I just get a single point and all information. That cannot be a way. So looking at the eigenvalues doesn't sound very useful in this case, or does it? A somewhat mysterious thing, which becomes clear with foresight, is that instead of just looking at the eigenvalues of the entire matrix, where there is really no additional information, how about I look at all leading principal minors, eigenvalues of all the leading principal minors of this matrix on the manifold. So here's a example of a 3x3 matrix. So this matrix X, which is represented here, sits on the orbit. And what I've written down here are the eigenvalues of the principal leading minors. So this orange block here is just a 1x1 matrix. Its eigenvalue actually is x11. Nevertheless, I call it R11 for some reason, which will become clear. The 2x2 matrix, which is in blue here, its eigenvalues are listed here. And in fact, I choose to list them in decreasing order. And similarly, a 3x3 matrix, which is the entire matrix in this case, its eigenvalues are also listed here. Now, I do know the boundary condition that the eigenvalues at the end, which is the eigenvalues of the entire matrix, are the same as the eigenvalues lambda i's of this given matrix lambda. Okay, but I know, at least in the 3x3 case, it's not super interesting, I must say. But I know that R11 is X11. But there is still some freedom that you have here. So this is a useful fact, I think, for people who are dealing with matrices on a regular basis. It's an independently useful fact that just given these R values, okay? So we have two ways to represent a matrix now. One is in terms of these coordinates, and one is in terms of these eigenvalues of all leading principal items. That you can actually recover essentially all the information there is in the matrix from these eigenvalues. And I say essentially because there are a few caveats, okay? So I can recover the eigenvectors up to a complex sign, essentially. Now, the question is whether this complex sign is crucial for the kind of problem that we are looking at, and the punchline is it's not. So this mapping, which is called the Rayleigh map, is actually is going to be sufficient for us to develop a sampling algorithm. So this is a major conceptual idea to start looking at matrix in from the in the coordinate reference frame, and stop looking at the matrix in the coordinate reference frame and start looking at it in the spectral reference frame. Other questions about what this mapping is? I understand that this fact is not really obvious. It requires, but it's not, I mean, it's elementary. It's not difficult. Okay, so if there are no questions about this map, let's keep going and let's look at what this map looks like in simple but important, already an open special case, which is the case that we talked about in the first slide of the talk, the case of rank 1 projection matrices or the rank 1 density matrices. This is essentially also the same as the complex unit sphere. So what does the Rayleigh map do for this manifold? So what are we trying to understand? We are trying to understand what is the image of this object, this orbit O sub E1 under this mapping. What is the object that we get? Any conjecture before I reveal the answer, what that thing might be on the audience? Or nobody's willing to take a risk at this time of the day, I guess. We'll see what the answer is. This is something that everybody here, I'm sure, knows very well what the object is.
Is it some chi-squared distributions, or what is it? Normalized Gaussians, right? I mean, sorry, it's chi-squared, I guess. So chi-squared, yeah, chi-squared.
So okay, so just to reframe the question a little bit better, we have this non-convex set, this orbit, right? And we are taking its image under this mapping. And my question is, what is the image look like? It's a set. Is it convex? First of all, if it's convex, what is it? So
yeah, I think what Ashwin said about the chi-squared should be the sums of each levels. Right. They should add up to this many components, but I don't know what the rest of them are.
Right. So it turns out that this will be the probability simplex in this very simple case, and I will show you how. The more general case is interesting as well, but I would not have time to go into the more general case. So, so to see that, okay, so I mean, I don't like having suspense beyond what's necessary. So here's the punchline, that this manifold, this orbit, actually maps to your probability density, probability simplex. And here is the basically the proof of this. So the first observation is, so X is a rank 1 matrix. In fact, rank 1 with trace 1. So it can only have at most one non-zero eigenvalue in any principal leading any of these matrices here. So in each of these rows that we see here, which are arranged in decreasing order, at most one entry can be non-zero, and that better be the first entry. Okay. There is something that I have not talked about so far, and I will mention it in my next slide, but I think it's useful to know here that these numbers are also related across the rows. So we have these inequalities which are in each row. I know that these numbers are decreasing, but I also know from very basic linear algebra that these rows interlace with each other. And what that means is that this number is in between this number and this number here. This number is in between in this number and this number. So in particular, what I get is that this number is at least this number is at least this number, and that's what I have written here. Okay, so I have these inequalities here, I know that this thing is 1 because the trace is 1, and this is exactly one non-zero eigenvalue. So what I could do is I could take the differences of successive entries here, like I do here, and just and observe that this is actually nothing but the diagonal of this matrix. So this may be a little bit confusing way to say that, but this is one way to say that. And as a consequence, you can check that the sum of all these numbers is, well, you can already check from here that the sum of all these numbers is 1. They're all non-negative because of these inequalities, and they sum up to 1 because every alternate thing will cancel. And so you're left with essentially this should be equal to 0. Yeah. Yeah. Okay, so this is maybe a little bit sketchy, but still, I think this is not too hard to convert into a formal proof. And so there is an interesting thing that happened here. We started off with a manifold, which is non-convex. In fact, it's but it has structure. It's a unitary orbit. We defined a mapping, this Rayleigh map. And when we looked at the image of this orbit under that map, we get a polytope. In fact, in this simple case, the simplex. I mean, this is really remarkable fact, and this is very, very general. For people who are familiar with symplectic geometry in the audience, have heard of things like moment maps and so on. And this is a type of these Atiyah convexity results and so on, costant convexity results. This is an example of that type of result, but it's not the same because moment maps just map to the diagonal. This is a more complex mapping. So the question is, what happens in general? And what happens to the distribution, which is what we should not forget. I mean, this is all nice, beautiful mathematics, but we are really interested in understanding the distribution. So, so here are some facts, which I've already explained in the context of rank 1, in the rank 1 case. These polytopes have a name. They're called Gelfand-Cetlin polytopes. In fact, they have their special types of flow polytopes, which is, I see a bunch of people in combinatorial optimization in the audience. So they have structure even as polytopes. These are not just arbitrary polytopes. They have a lot of structure. And in fact, by basic linear algebra or Cauchy interlacing theorem, you can show that these, what I just claimed before, that these inequalities, actually there are inequalities across rows. So you see a whole bunch of inequalities in this on the right-hand side of this picture, and these are exactly the defining inequalities of the polytope. There's nothing else left. Non-negativity, this boundary condition, interlacing conditions, and decreasing. So this is the polyhedral description of this polytope. So beautiful connection between a discrete object and a continuous object, and this is not an accident. This is a consequence of the connection between Lie groups, which are continuous objects, but the corresponding Weyl groups, which are discrete groups associated, or in some sense, which exactly capture the Lie group. Okay, so what about the measure? Beautiful fact again, that if you look at the uniform measure on this polytope, it actually projects onto exactly the uniform Lebesgue measure on this GT polytope. Something that is not true for the moment polytope, if there's somebody here in the audience who knows what that object is. And that is why we are using these objects. And even more so, the exponential density that we were looking at, which is what our goal was, actually maps to an exponential density on the GT polytope. So remember that this GT polytope, this Gelfand-Setlin polytope, sits in your standard Euclidean space with Lebesgue measure. So this might, if this is too funky, then this is all very standard. Okay, so the goal, what we have done through this is to reduce the density on a manifold to a very precise density on the polytope. And so at a high level, this suggests the following approach. Okay, there's another observation which is probably not going to add any more value to this discussion already, but the density is also constant on the fibers, and I'm going to tell you what these fibers are in a second. So here's the high-level algorithm. That to sample from the orbit, you first sample from the corresponding GT polytope. So we will have closed form expressions of all these exponential density and so on in terms of the given matrix Y. So we sample from this exponential density on the GT polytope, and then we pull back this distribution to the orbit. And that corresponds to sampling a matrix S from this fiber of the Rayleigh map. So the Rayleigh map is not a one-to-one map. It has a fiber. And so we need to be able to go back. So we need, once we have a point R in the GT polytope, we need to sample a random point from this fiber, which is again a continuous set. And we can do both of these steps, and that's really the main technical contribution of the paper, that we can write down efficiently computable expressions in terms of ratios of determinants for each coordinate of this Rayleigh. This is also called the Rayleigh triangle. It looks like a triangle. So you start sampling one by one and row by row, and then in each row from left to right, and you can we can write down a precise formula which is efficiently computable using determinants for each of these coordinates. In case you're wondering what this looks like, the rank 1 case, the measure is actually very simple. There's nothing funky that happens here. The rank 1 case being the simplex case that we talked about. So there's just, without loss of generality, because of unitary invariance, we can assume Y is diagonal. And once we assume that, X is just the diagonal of X. So this just becomes the standard inner product in the Euclidean space, and you get an exponential density, and you want to sample from that. And these conditioned CDFs that I talked about actually have a nice recursive structure in the case of simplex, and we can write down exact formulas for these densities. And once you have exact formulas, you can use the inverse CDF method to sample. So this is all I'm going to talk about, the sampling, and I'm going to zoom out in the next couple of minutes. So if there are any questions about this high-level approach to sampling, I'll be happy to answer now, or come back to it later. But really, yeah, the main technical contribution is to write down these formulas for general GT polytopes. Okay, so let's go back to this quantum inference problem that we started off with. So remember that we were given this density matrix, and we were our goal was to infer a rank 1 density matrix. And we approached it from the maximum entropy principle. And the dual of it, you may ask, how do I solve this optimization problem? That's a story in itself, which was done with joint work with Jonathan Leake in an earlier paper. And it uses the ellipsoid method in the space of matrices. There's nothing non-convex about this set. It's all nice and convex. The problem here in solving this optimization problem is, one, that since Y is unconstrained, we need some bound on how big the norm of the optimal solution is going to be. We need some bounding ball to deploy ellipsoid method. And that's one major contribution of this work. And the second is that we need to be able to evaluate the objective function and its gradient to get the separating hyperplane that we need for the ellipsoid method. And this reduces essentially to evaluating these kinds of objective functions, where the hard part is really just the integral. And this is this turns out to be related to the kind of integrals I was talking about in my previous slide. So some very special cases of this integral formulas were already there in this paper before. And once you have this optimal Y star, then you could, using this high-level algorithm I talked about before, sample from this density. Okay, so I'm, I think, out of time. I'll conclude. The main result is a polynomial time algorithm for sampling from these density functions, which have various applications in actually many domains. So they seem pretty central, and I suspect there will be more applications of this density function, at least in theoretical computer science, and perhaps in quantum computing. The result technically relies on some beautiful connections between unitary orbits, polytopes, measures, determinants. So very nice interplay between discrete and continuous. The result extends to other classical compact Lie groups. And I guess the take home is, if you have an optimization or sampling problem over a manifold, typically involving matrices, it's worth asking yourself, are there invariants? Are there symmetries? And I think this paradigm has been recently been used in other problems in theoretical computer science as well. So I'll stop with that. Thank you so much for your attention. And these are the links for the papers in case somebody's interested in looking at them. And I'll stop for questions.
Thank you, Nisheeth. So any question from the audience?
Yeah, I had one. Could you say a little more about what is it about the structure of these GT polytopes that allows you to do exponential sampling?
What is it about the structure of these GT polytopes which allows us to do this exponential sampling? Is that the question?
Yeah.
So I don't have a very easy answer for that, to be very honest. The simplex case which I illustrated tells you that, I mean, yeah, so once you're conditioning, you're essentially slicing the polytope, right? And in some sense, let me go back actually to this definition. So in some sense, one answer could be, your question is that if I condition row by row, then I keep getting GT polytopes again. So if I condition this row, this small thing above it, entirely above it, is also a GT polytope. If I condition these two rows, then what I get here is also a GT polytope. So there is a recursive structure. So it does tell you that the unitary orbit, a unitary orbit can be written as direct sum of unitary orbits where the action is with respect to un minus 1. And that's what is revealed in this Reale mapping. I don't know if this was a satisfactory answer to your question, but this is the recursive structure we were looking for, and that shows up in the GT polytope. So GT polytope themselves are recursive objects in the sense that I described. That by fixing rows or slicing the polytope across by fixing elements of these each, the full row, you get back again a GT polytope. One challenge we have in our result is because we cannot fix the entire row at once, we have to do it coordinate by coordinate. So we have to look at slices of GT polytopes, which are not quite GT polytopes. And that's why we need ratios of determinants. Yeah.
Thank you.
Other questions?
Well, I was actually, I was going to ask about this fact that determinants come into the sampling problem. Is there a relationship between those determinants, or can you interpret them as arising from some kind of system of fermions?
I'm sure you can, except I mean, you know, I know all these keywords and I know enough to say that I'm sure you can, but I don't know enough to say how. In fact, there is, yeah, the fact that determinants show up is actually quite remarkable. So I have to, you know, I have to show you this. Let me just try to go to this. Yeah, this slide here. So if I look at this integral here, if you can see my cursor, this is an orbital integral over a Lie group, and it is known that you can write this as a discrete summation over the corresponding Weyl group. So a Weyl group of a Lie group is typically some exponential size object like Sn, the set of all permutations. So there is this very deep and beautiful connection, and that was discovered by Harish Chandra in a very general setting. That for a general semi-simple Lie group, you can write down these orbital integrals as sums over their Weyl groups. It turns out that for the unitary group, the corresponding Weyl group, I believe, is just Sn, the symmetry group. And that is what gives rise to the determinant. So in some sense, this is really takes you to the representations of this of the unitary group, and that's where the symmetry group shows up, and that's why the determinant shows up and not the permanent, for instance. I mean, for all you know, you might have gotten a permanent and not a determinant. So it's really a miracle that you end up getting a determinant here.
Thanks.
Okay. More questions? All right, so if there are no more questions, let's thank Nisheeth again for the nice presentation.
Thank you.
Okay, and yeah, Nisheeth, just feel free to stay for a little bit if you like, or you don't have obligation.
Yeah, I'll hang out for maybe a few minutes in case.